keynote speaker, Professor Fabrizio Piacentini. He's from INRIM. I mean, I cannot exactly pronounce this one. It's a defense institute from Turin. It's really a huge institute and a huge funding and huge number of labs, and there's a lot of setups. I visited once in 2009, I think. That time also they had equipments and that we cannot see, and we cannot imagine such kind of setup they have. And Fabrizio is from there, and he's actually from this group, the Marco Genovese group. It's a very famous group in Europe. So he will be talking about today regarding the weak measurements, and he wants to say that this is actually the new technology we developed through the weak measurement. So Fabrizio.
Okay, thanks Alok and all the organizers for giving me the chance to speak at this beautiful school and conference. I'm pretty amazed from the numbers that Alok told me about of students and everyone that wants to participate with it. And I will now share my screen. Okay. I think everyone is okay
yes,
now.
It's a full screen. Make it full screen.
Is it full screen? Is okay now?
There is a right side, something is coming. So yeah.
But okay. Then let me just go out for of this full screen. I will just try this screen here. And now it should work.
Yeah, it's okay. It's a full screen. I think this yeah, it's working.
Okay.
Move a couple of slides. Let's see.
Yeah, I will just remove this.
Up and down.
No, it's okay to put it here.
Okay.
Is it everything okay? Do you see my screen?
Yes, perfectly.
Okay.
Okay.
And as Alok said, I will talk about not just weak measurements, but weak interaction-based measurements as a new tool for quantum technologies, as well, of course, as a foundational research tool. Okay, first of all, we all know that we are in the middle of the new quantum revolution that ranges from quantum metrology and sensing with in vivo optically detected magnetic resonance, sub-shot noise imaging, to quantum information. As everybody can recognize here, we have the recent uproar in quantum computation with the photonic qubits quantum supremacy reached in China. We have, of course, quantum communication with quantum nectars arising in many cities around the globe. And of course, we still have quantum foundations investigation as the loophole-free Bell test and many other like contextuality tests, macro-realism tests, and studies on the wave function, collapse, and whatever. And we all know that quantum measurement features can overcome, in some special cases, the limits of classical systems. So this makes them a huge tool also for just practical technological improvements. Just like, as I said, sub-shot noise imaging, able to give the image of very photosensitive molecules, or that could be essentially degraded even by the faintest laser that one could apply. But okay, quantum measurement is a big word. So let's begin with defining what every student knows, the traditional or sharp measurement in quantum mechanics. We know we have our operator that could be decomposed in a series of projectors, and we have the Born rule, with rho being the density matrix of the state on which the measurement is carried on. And we all know that a single, for example, projective measurement gives us the eigenvector the corresponding to the obtained eigenvalue, with a probability that is given exactly by the Born rule. But what happens if I want to do a second measurement on my system? If I have a scheme like this, do I have this? Of course, the answer is no, because what I have is this instead. And why do I have this joint probability? I have this that is completely different from the trace that I wanted before, because of the wave function collapse. After the first measurement, I don't have rho anymore. I have already the state psi k, psi k. And so the second measurement is not carried on the same state because because of the wave function collapse, non-commuting observables can't be simultaneously measured. And this is true, but this condition can be relaxed in one way. Which way? By exploiting exactly weak measurement. Weak measurements have been introduced in the late 80s by Aharonov and Albert and Bellman. And they are a protocol in which a little information is extracted from a single measurement event, essentially a very tiny amount. But what you gain is that the state does not collapse. We avoid wave function collapse by inducing only a small decoherence on our quantum state. And from weak measurements and a subsequent post-selection, we can extract a new mathematical element that is the weak value. As you can see, it's quite similar to the expectation value, but while the expectation value has the same state on the right hand and on the left hand of the operator, here we have two different states, psi I and psi f, divided by the internal product of those two. Psi I is the pre-selected state or initial state on which the operator acts. And then we have psi f. Psi f is exactly the post-selection, the strong post-selection that is that occurs after the weak measurement. From this, we can obtain this exotic tool that, of course, collapses to the expectation value when psi f equals psi I. But how do we do this? We make a von Neumann coupling between, we make an indirect measurement that consists of a von Neumann coupling between the observable of interest, that is A in this case, and a pointer observable that we will call P. Then we make a projective measurement on the A subspace, not on the P1. And what we extract is that we have at the end of the whole measurement procedure, we have on the a global wave function psi out that is given by this function. As you can see, we have the component psi I that refers to the Hilbert space of A, and the component phi p that refers to the Hilbert space of the pointer P. And in the weak interaction approximation, that means when G goes to 0, we can perform a series development, and what we obtain is that if we compute the average of the x, this canonically conjugated with P, what we obtain is that x, the average value of the observable x, is proportional to the real part of this weak value. And this already could sound strange because usually when I deal with quantum measurements and I deal with average values, expectation values, or eigenvalues, I never need to specify a real part. Why? Because everything is real. Otherwise, it's inconsistent. It would be inconsistent quantum mechanically. And this is the first astonishing property of weak values. They can be a complex number. Not only that, even the real part can be unbounded. In fact, in their seminal paper from 1988, Aharonov, Albert, and Weidman chose as a title, how can a spin 1/2 particle spin component on the z-axis be 100? Because even the real part of the weak value can be very far from the boundaries of the eigenvalues spectrum. Okay, There have been many interpretations of weak values, and there are nowadays, even there is a huge debate still ongoing about them. For example, the real part of the weak value could be a conditional average in the limit of zero disturbance, while the imaginary part could be arising from a disturbance related to the von Neumann coupling between the observable interest and the pointer observable. Then, of course, mathematically, it's easy to prove that expectation values can be observed and computed as averages of different weak values, and POVMs themselves can be realized as a sequence of weak values. Okay, this is a very general perspective, but now let me tell you one of the strategies to realize a weak value. And being a quantum optics researcher, I will tell you about photopolarization. We have an initial state, psi in, with two components, one pertaining to the polarization observable, that we chose to be linear polarization without loss of energy rarity. And the other one is the spatial component, because what we will do is couple the polarization degree of freedom to a transverse degree of spatial degree of freedom of the photon distribution. This is the scheme. We have our initial photon going through a birefringent crystal that realizes the von Neumann coupling between A, our observable, in this case is the vertical component of the polarization, and P, that here is the transverse momentum on the direction, on a direction orthogonal to the photon propagation direction. Then, in a second in a subsequent time, we have a polarizer realizing the post-selection onto the A, on the A Hilbert space, on the polarization Hilbert space, and a detector, a spatial result detector that is able to observe, to measure the spatial shift induced in the polarization by the von Neumann coupling. We measure the position observable X, canonically conjugated to P, and what you observe, as I told you before, is that in this case, X would be proportional to the weak value of the polarization component. Okay, so far so good. Let's talk about possible applications of weak values. For example, we have metrology. I'm from a metrological institute, so I have a keen eye on that. And there have been many experiments on that. And the most famous phenomenon and effect that we have is an amplification of measurement of coupling strength. We have this tiny coupling, that is G, and if we want to measure this tiny coupling, we can, with weak values, we can overcome technical noise unrelated, that is unrelated to the quantum effects, and we could get rid of it, or at least overcome some of the limitations of that could occur with traditional measurements by exploiting weak values. We have a magnification and amplification effect. Then we have, this has been used for light beam displacement, for angular deflections, for phase estimation in many fields. Then, as I had to choose just a few examples because there is a huge literature already on this field. Then, of course, we have quantum mechanics and foundations investigations. We have, it has been done a direct measurement of the wave function from Charles Bamberg's group. Then there has been a huge research on sequential and joint wave measurements that's allowed to measure incompatible and non-commuting observables on the same particle, on the same quantum state. We have, it has been proposed by Mitchison, Joseph, and Pescu, for example. And it has been realized by us, by Landin's group, Jeff Landin's group, and by Cho and Kim group. And so then we have, let me tell you about just one hint about this. That is the one that I know best, of course, because I'm one of the people that realize this. We have obtained it at the real single photon level, I mean with certified single photons, and we have measured two orthogonal polarization axes, two non-orthogonal, sorry, polarization axes. One is the vertical one, and the other one is a polarization on whatever angle theta. The scheme is this one. Of course, we have a first measurement realizing the coupling between pi v and the y direction, being z, the propagation direction of the photons. And then we have a pair of a second weak measurement station with the coupling on the x-axis, and two halfway plates rotating the polarization plane, allowing to realize that the pi theta operator. And what we obtain is this. As you can see, here we have pi v, the weak value of pi v, the weak value of pi psi, and the weak value of their product. Not only we can measure the weak value of two non-orthogonal observables, but we can also measure their product, that is not even an Hermitian operator. And what is most interesting is that we have learned at school that minus a negative number multiplied by a positive number makes a negative number. But look here, a negative weak value times a positive weak value can give a positive weak value. This is a beautiful example of what is called product rule breaking. It is perfectly allowed in a wave-like probabilistic theory, but should not in a particle one. And this is an experiment that has been carried onto onto certified single photons, heralded single photons produced with parametric unconversions. So it cannot be an average effect, let's say. And then we have a side of measurements of non-commuting observables. We have, for example, quantumness tests in several scenarios, like contextuality, that has been realized by and debated in different ways, or Leggett-Gard inequality tests, like the first one from Gogin et al. And the subsequent one made by our group that extended the alphabet of the previous experiment. Essentially, usually Leggett-Gard inequalities have three coefficients with correlation coefficients between among three operators. Sorry, and what we did here is extending the alphabet to four operators, obtaining a sort of temporal CHSH that could be obtained at the single photon level with certified single photons still by exploiting sequential weak measurements. Originally, Leggett-Gard inequalities were proposed for macrorealism tests. Of course, we don't have a beautiful big Josephson junction, and this cannot be regarded as a macrorealism test anymore because photons are not macroscopic objects, of course. But it's still a quantumness, a very valid and trustworthy quantumness test. And by exploiting sequential weak values, we can obtain an inequality like this one, where we have IA, that is the preparation of our system, IC and IB, that are two intermediate sequential weak values on non-commuting observables, of course. And then a ID is the post-selection. By evaluating all these correlation coefficients, what we obtain is this. This is the shape of the bound before, that is the term of the inequality. The yellow region is where the inequality is fulfilled. The orange is the place when the upper bound is violated, and the purple one is the lower bound violation. What we measured here is by choosing alpha and delta and gamma carefully, is this violation here that is perfectly in agreement with the quantum mechanical prediction, but it represents a strong violation of the classical bound, let's say. Not only that, while in the experiment from Gogin et al., the violation of the Legge-Garg inequality was had a deep connection with the anomalous weak value being measured. That means that you could have a violation only if and only if an anomalous weak value could be measured in the setup. Here we have a different scenario. That means that the weak value, being anomalous, is a necessary but not sufficient condition for observing a violation. We could have anomalous weak values and still fulfill the classical bound. So it's a little bit different framework that could be due to the fact that even operators, multiple measurement Legge-Garg inequalities have a double bound. This relation could be due to that. Okay. Then we have a huge debate on quantum mechanics interpretation related to weak values, stating with the two-state vector formalism from Arnold and Bedman co-workers, and that is still undergoing a huge debate, as well as as the quantum or classical nature of weak values or statistical nature of weak values, and so on. So to resume this part, we have that weak values that we know very well what they are. They are a new tool for quantum mechanics, as well for the practical application as well as for the foundational aspects. They can be anomalous, complex or unbounded, whatever. They can be used for metrology and for quantum mechanics and foundational aspects. But my question is, what's beyond them? Is there something that can be regarded as a sort of step forward, a sort of evolution of weak measurement and weak values? In the remaining part of my talk, I will present you 3 answers to these questions that have been obtained in our labs. The first one is the implementation of a protocol proposed by Lev Weidman, these protective measurements, realized for the first time in our lab. Okay, let me ask you one thing. Is it possible to extract the quantum expectation value of an observable by measuring a single particle? I mean, I give you a single particle, you do whatever you want with your black box, with your measurement, and you extract me at the end of that that single particle measurement. You have as an outcome already the expectation value. Heuristically, one could say no, because you know that you could obtain eigenvalues from measurement. But this is not the case if you apply protective measurement. Protective measurement is not only able to leave the state unperturbed during the whole measurement procedure, thanks to the interaction being smooth and faint throughout the process, and thanks also to the presence of a protection mechanism that is preserving the coherence of the state during the measurement procedure, but it also gives a pointer shift proportional to the average value of the measured observable. What does it mean? Let's say that we are measuring the polarization of our photon. In a projective measurement scenario with a very thick birefringent crystal, we would have this picture, a very Stern-Gerlach-like picture, and then we compute the number of minus A event, the number of minus event, the number of plus events, and by them we obtain the expectation value of the polarization. Okay. Instead, with protective measurement, what we obtain is this. As you can see, all the photons coalesce in a specific position that is not related to any of the eigenvalues of the plus or minus one eigenvalues related to the operator that we are measuring, but to whose position is proportional to the expectation value of our polarization, of our observable of interest. This means that I can still keep my acquisition on to just accumulate statistics and have a more precise measurement. But even one single particle impinging on my screen already allows extracting information, reliable information on the expectation value. Okay, so this is a quite astonishing feature. One of the possible implementations of protective measurement is this one that exploits active xeno-like protection. What does it mean? I have my first, on the left, my first selection that is realized by the purple filter, polarizing filter. And then I have a sequence of identical steps. Each step is composed by two parts. The first one is the weak measurement, the weak interaction part, let's say. And the second one is the xeno-like protection, is a xeno-like protection. That means a projection onto the initial state. Of course, if G is faint enough, in the ideal case, the number of steps K would be infinite, G would be 0, so there would be no losses. With a photon survival probability that is 1. The photon survives until the end, remaining completely unchanged. This is a beautiful feature, but of course for an experimentalist like me is quite a difficult one. That's why from the beautiful theoretical asymptotic limit that we have that we presented before, we go to a more sloppy one. Let's say it's not the right term, but it's funny to say that keeps us with our feet on Earth, with just K equal to 7 and a very faint G, much smaller than 1, but not 0, with a survival probability that is at the Kth step that is not exactly 1, but close enough. The scheme is this one. We have a heralded single photon source realized through type 1 parametric time conversion. And the photon at 920 nanometers heralds the presence of its twin on the other arm. The other twin is fiber coupled, and then decoupled in open air to make the experiment, collimated in a Gaussian mode. We have an initial preparation stage, and then a sequence of 7 steps, each composed of a pair of birefringent crystals and the polarizing plates performing the protection, while the birefringent crystal pairs performs the von Neumann coupling. Why is there a pair here and not just a single crystal? Because we use the first crystal to perform the von Neumann coupling and the second one to compensate for time and phase decoherence induced by the first crystal. Okay, so far so good. And of course, if we want to compare the protective measurement features with the projective measurement one, what we have to do is just remove the protection realized by the polarizing plate. And that's what we did. And this is the part regarding the quantum state protection, because first of all, we put a quantum tomography apparatus at the end of our process before the detector, the two-dimensional spatial resolving detector that we had. That is not a common detector, is a SPAD array. I mean, we had an array of single photon avalanche diodes, of single photon detectors that gave us two-dimensional spatial resolution on a 32 by 32 array. Of course, with projective measurement, at the out of the process, so without protection, we would have we expect to have a density metric like this one, with a decoherence term depending on the final coupling, that is the sum of all couplings through the case steps. While with protective measurement, because of the protection mechanism, we don't expect this decoherence to occur, and we expect to have something very close to the initial state that we prepare inside our experimental setup. To observe this, we perform quantum state tomography, and we evaluate Ullmann's fidelity and purity of the state. What we obtain is this. For this specific state, it's just an example. We did it for different states, but I just wanted to give you a specific result. We have, for a projective measurement, these states, where on the left, we have the real part of the expected density matrix. The imaginary part is 0, so I didn't report it. As you can see, the projective measurement seems to behave quite as we expected, and protective measurement as well. We have reported the initial state real part, and the reconstructed imaginary and real part of the density matrix outgoing the protective measurement. As you can see, even by eye, the fidelity is almost absolute, and these are the computed numbers. Everything is, for example, every protocol was performing with a fidelity of above 99%. But as you can see, the fidelity between the initial state and the one outgoing projective measurement is quite low, 0.75 as expected. And concerning purity, the purity of the state outgoing protective measurement is still above 99%, while the one outgoing projective measurement drops to 50%. This means that we managed to testify how protective measurement really protects the quantum state from the coherence. It starts pure, it ends as the same pure state that was initially prepared. This, of course, does not hold for projective measurement. Okay, then what about the expectation values? We have the same state, giving an expectation, theoretical expectation value of minus 0.2. And this is the picture that we obtain with projective measurement. As you can see, you can perfectly identify the vertically polarized photons region on the left, the horizontally polarized photon region on the right. And from them, while for protective measurement, all the photons coalesce in a single position. And this position is not perfectly centered. As you can see, it's slightly shifted on the left, as one should expect. In fact, if we compute the expectation value with both protocols, what we obtain is a value that is perfectly compatible with the theoretical expectation, and also perfectly compatible between themselves, testifying that both measurement procedures are perfectly capable of performing their task, but protective measurement can allow extracting that same value, of course, not with this uncertainty, even with one single detection event. This is even more evident if we look at a few events picture, like this one for projective measurement. This is a raw image. We didn't even clean it from dark counts, as you can see from the firing pixel on the upper part of the screen. The dashed line, dashed vertical line, represents the expectation value that we're supposed to measure. And these pixel firing, as you can see, are firing as where they should, because the red circles represent the 1 sigma, the limit distribution of the vertical and horizontal polarizations in our screen. But with a single click, we couldn't say anything. For example, the first click of this acquisition was the white one on the left. How could such a measurement procedure give us any hint on that yellow dashed line? It's impossible. But this does not hold for this. Okay, here it is a little more noisy. We have many more dark counts, but this is a problem of our instrument, not related to our procedure. But as you can see here, all the photons fall in a specific position, and from each of them, one could rely a quite reliable estimate of the expectation value that we want to measure. We were especially lucky because in the first firing pixel, the white one, was very close to the expectation value that we wanted to measure, that we were supposed to measure. But anyway, each of them can give an estimate of that. Okay, these are the results that we obtained for the rest of the states that we measured. As you can see, all of the results, of the experimental results, are in perfect agreement with both the theory and the two protocols that were employed to evaluate the polarization average value. But there is another thing that I ask you to look at. In all these cases, the uncertainty related to protective measurement is equal or below the one given by projective measurement. As a metrologist, this should make some bell ring. And this happened to us. We asked, okay, is this just pure luck, or is there something non-trivial behind it? How accurate can protective measurements be? And to give an answer to this question, we compared the uncertainty on P given by a K-steps protective measurement with the one obtained with a projective measurement. And we computed this ratio R that tells us that everything going above the pink plane in this picture here is already advantageous for protective measurement. And here we have, these are theoretical calculations. We have the yellow plane, the yellow curve, sorry, that is for our case, k equal to 7, and then an asymptotic behavior with k equal 100. And for k equal 100, we have a maximum advantage that is about 8.5. But 8.5 more advantageous with respect to projective measurement, it means almost 1 order of magnitude. And how can this happen? How can this happen? Do not projective measurements saturate the quantum Kramer-Rao bound? Should they not be the ultimate precision? Because these are computations, these calculations are telling us that, okay, there is the ultimate precision is not reached in this case by projective measurement. Protective measurement are even advantageous, are already advantageous in our case, k equal to 7, but they're disruptively advantageous for large k. And not only that, look at the G on this screen. For G equal to 0, going to 0 or below 1, one could expect this to happen because, okay, you have faint interaction, you have a protection mechanism, you don't lose your photons. But for G equal to 8, you're already outside the protective measurement framework because your G is strong, is big, so you're not employing a weak interaction. We perform a sequential measurement, but not anymore a protective measurement. You're not preserving the state, your survival probability is not 1 or close to 1. You have losses. How can a lossy protocol be advantageous? Because this curve here has been obtained considering the same amount of initial photons. I mean, if we don't, if we use a protective measurement with a projective measurement, you know that in a theoretical picture, projective measurements are losses. I always observe my photon. I have a PBS. It either goes out from one path or from the other, but it's I can still observe it. And this could not happen with protective measurement or with, especially when increasing G. So we consider a number of initial photons equal to the inverse of the survival probability of the photon through the protective measurement protocol for both protocols, so that the comparison was fair. The same amount of photons, of initial photons, for both protocols. And this is astonishing. It's astonishing also because it seems that, as I told you, if you increase, if you arbitrarily increase G, you have an asymptotic behavior, but still you preserve your advantage with respect to protective measurement. And by this observation stemmed the second answer to the question, what's beyond them? And the second answer is a protocol that we devised at INRIM after working on protective measurement, and we called it genetic quantum measurement. And well, let me tell you why by explaining what genetic quantum measurements are. First, let's toss a coin, quantum or not. With a classical coin, we have a binomial probability of having n heads over m tosses. And we can compute a coin mean fairness parameter that is related to some uncertainty given by that equation on the right. What does happen with a quantum coin? We have a quantum mint, for example, state filtering. We have our PBS. We have the quantum mint preparing the photon in cos theta heads plus sin theta tails. And the quantum mean fairness observable will be the S operator. And the quantum Cramer-Rao bound tells us that the ultimate precision that could be reached is US, where the J being the given by 1 over the square root of MJ, with J being the quantum Fisher information given by this scenario. So quantum coins seem to perform exactly like classical ones. As I told you in the initial, at the beginning of my talk, quantum mechanics can be advantageous in some specific cases. And this seems to be one of the cases in which quantum mechanics is not advantageous. But is it the case? Let me illustrate you a new paradigm, a new measurement paradigm that we call genetic quantum measurement. This is a sort of paradigm shift. We have case steps, and we relax completely the hypothesis on the weak interaction. Instead, here we have a strong interaction. We have our quantum mean, our state filtering, and then we have a sequence of steps identical to the ones used on the Zeno type implementation of protective measurement. But here the interaction between the measurement apparatus and the quantum state is not anymore faint, and it separates completely tails from heads. And then we have again a state filtering identical to the initial quantum mean. Here we have the interaction, not weak anymore, separating them. On the second step, after the first state filter, of course, here we don't have any weakness anymore. So the state filtering is a lossy procedure. Every time I apply pi theta, I have losses. But from the second step onwards, I don't only have the interaction separating tails from heads. As you can observe from the yellow circle, I have a coherent recombination that works like a superposition or interference between the heads and tails component of the wave function. And here in this specific step, I have psi theta, that of course is unaffected by the state filtering. On the third step, I still have the interaction, the separation between tails and heads, but also some recombination that is not giving, that are not giving any more psi theta, but different states with different theta parameters. Okay, if I apply this for a sequence of steps, what I obtain is a sequence that in some sense mimics the mutation, selection, and crossover mechanisms typical of a genetic evolution, or typical, for example, of the one of what we find or what you can find on genetic algorithm. Not only that, if we regard to this scenario as some sort of evolutionary trajectories for our quantum coin, thanks to quantum parallelism, all these trajectories are sensed simultaneously until let's say the until the photon or the particle, let's say, is detected. Of course, we have a survival probability now that is not one anymore, and it is given by the non-normalized, by the trace on the normal normalized state psi out, given by this formula here. And we again computed the same calculation, the same R factor for this scenario. This is the same. This is essentially the same figure as before. Of course, now instead of regarding the weak interaction regime, the small g regime, we regard the whole g axis. And as I told you before, for a fair comparison, we consider m initial photons. So a number of photons that is the inverse of the survival probability at the end of the kth step for the genetic quantum measurement procedure. Also for the projective one that we call the PBS, because we gave the initial example of the polarizing beam splitter acting on the quantum mean. And where does this advantage stem from? Because we still conserve this advantage. Well, let's perform well, I give you immediately a hint. This advantage stems from the fact that if k is great, is large, the survival probability at the k step is much larger than the survival probability at the first step elevated at the kth power. Because heuristically, one could think, okay, let's have a balanced coin that is with a g, and let's use a g much greater than 1. Of course, if I have a coin of this type, the survival probability to the first step is 1/2. And one could think, okay, if I have 100 step, I should have 1/2 to the 100th power, that is more or less around 10 to the minus 30. Okay. What would you say if I told you that this is not 10 to the minus 30? This is 5%. We are 28 orders of magnitude above what can intuitively be expected. 28 orders of magnitude. Of course, when we saw this, it was Friday. I can remember. I still remember it. We said, okay, we're tired. Let's go home and come back on Monday. We will laugh at ourselves and how dumb we were when we performed this calculation. But on Monday, these results were still there, and they were confirmed. This is the survival probability for k equal to 100. As you can see, it never drops below some percent. And to test this, perform an experiment with a setup that is almost identical to the one of protective measurement, but in which we use, of course, instead of heads and tails, we use H and D, the polarization of the states. And we don't use anymore a very faint G. The results are this one. These are the states. This is these are the uncertainties, the curves reporting the uncertainties related, associated with the GQM procedure and the PBS procedure to the polarization P. That is what our observable S becomes when dealing with photon polarization. The vertical planes are referred to the states that we exploited in our experiment. And from that, we obtain this. As you can see, in almost all of them, in 8 cases over 9, the projective measurement is disadvantageous with respect to the protective one. Why? Because it offers a larger uncertainty. This does not occur only in the bottom left point. Why? Because the resolution, the G here was not enough to have a proper resolution for the set, but it's still comparable. So it seems to be always advantageous or at least comparable. And this can be even clearer by looking at the R ratio. This is the R ratio for K equal to 7, like in our case. Again, the vertical planes are the ones regarding our states, and the purple plane, the horizontal one, is the threshold between the advantages, the genetic quantum measurement advantage and the projective measurement advantage. As you can see, again, we already have an advantage, an uncertainty reduction of a factor of 2 just with K equal to 7. A factor of 2 is already large, but with K equal to 100, a factor of almost 1 order of magnitude is what is called in metrology as a paradigm shift in precision measurement. So it's huge. It's really huge. But I was asking a question before. I was asking, how could this be? Projective measurements saturate the quantum Kramer-Rao bound. So they are optimal measurements in this scenario. So are genetic quantum measurement better than optimal? Is that what we are saying? Let's consider the uncertainty scaling with respect to the amount of initial states. In the PBS measurement, in projective measurement, we have a scaling of 1 over the square root of K with M equal to K. In genetic quantum measurement, we have the same scaling, 1 over the square root of K. But here, the number of initial states exploited for the measurement is much, much smaller than the number of steps K. And we have the same scaling. That's why it can be, it sounds advantageous. But how can this be? Well, this is the Fisher information associated with the POVM exploited for the estimation of the parameter lambda. The optimal estimation saturates, of course, saturates the quantum efficient information. But in genetic quantum measurement, we are outside of this framework because our POVM, because of the selection mechanism, is parameter dependent. So it simply performs better because we are outside the prepare and measure scheme. And the quantum Kramer-Rao bound does not hold anymore. New bounds have to be considered. Unfortunately, these new bounds are very difficult to compute and calculate, and a general form is looks like a sort of chimera to be found. And that's why, although the data on this, the last data on this experiment were collected 4 years and a half ago, we're still writing the manuscript, and we have not even an archive yet. But let's move on to the third and final answer to the question: what's beyond weak measurement? And this is a new measurement paradigm that can be considered a real evolution of weak measurements instead, not a weak interaction-based measurement. This is an evolution of weak measurement, and also a sort of generalization of protective measurement. Protective measurement allows obtaining the average value with one single shot. But can I generalize this to anomalous weak values? Is it possible to obtain anomalous weak values with a single photon detection? Well, the answer is, of course, is yes, if we exploit robust weak measurement. Robust weak measurement is an iterative protocol able to extract the weak value of an observable even from a single post-selecting quantum system. The scheme is like this. It looks similar to protective measurement, it's still an iterative protocol. But as you can see, here we have another item that performs the pre-selection. We have pre-selection, weak interaction, and post-selection. Let me remind you that although normally one could think that between post-selection and the subsequent pre-selection there could be losses, pre-selection is not a projection. In this case, it's just a unitary operation, lossless, preparing the state always in the same way, in this pre-selected state, psi I. Okay, if we have the same picture as the one that I presented you for protective measurement, what we should obtain is this. All the photons coalescing in a region outside the screen, or at least the screen portion related to the eigenvalues bound to the eigenvalue spectrum boundaries of my observable. And this position here should be proportional to the weak value that I want to that I'm expected to measure. Of course, if I present you this scheme, one could realize that, okay, this is equivalent to this. This is equivalent to having, instead of one photons coupled k time to the measuring device, it's the same as having k photons with a multipartite measurement device, and each photons is coupled to one part of this measurement device. So in this picture, it's only natural to measure as an observable this sigma 3 sigma, that is the sum of the polarizations of my k photons impinging on the measurement device. Of course, we will exploit the scheme above, but the two pictures are in complete analogy. So the experiment is this one. Now we have a photon source. This is the while the other ones were doing with the certified with the heralded single photons. Since here we had to substitute the SPAD array with the EMCCD for signal to noise ratio reasons, we have still a photon source that is attenuated at the single photon levels, but we don't have heralding anymore. We monitor the source, still obtained with parametric down conversion, to observe that it is still kept at the single photon level, but we don't rely on heralding. Anyway, the results are perfectly compatible to the scheme, to the ones that we obtained with that we could obtain with the heralded photons. We have 7 k equal to 7 weak measurement blocks, each realizing pre-selection, weak interaction, and post-selection. And of course, to achieve a high resolution, we should ask for small g and large K. But because of post-selection being different than pre-selection, this would mean huge losses. So high survival probability would require a small k, and even, I would say, a not so small g. So this trade-off is what conditions the resolution and the choice of parameters for my experiment. And to choose the best g for a number, for the suited number of steps k that we want to have, we rely on this. This is a study on how weak could a weak measurement be, because of course the finiteness of g does not compels us to restrict ourselves to a certain number of weak values before the linear approximation is not valid anymore, as you can see in this work here from our group. And once we chose the proper g and k, we moved to the experiment and we started to see ghosts like this. And ghosts may be scary, but there are times in which they can also teach you something. And by trusting our experiment, as an experimentalist would do, we went back from scratch to our calculations and we obtained this. This is our observable sigma 3 sigma normalized on the number of k particles or steps that we have. And what we obtained that are these curves here. And these curves here represent how far we go from the theoretical value of the weak value that we are supposed to expect when g grows depending on the number of k. As you can see, it's a strongly nonlinear function. And not only that, look, if I have g about 0.35 with k equal to 1, I have a slight deformation, but still it's reasonably close to a Gaussian. With the same g, this is what happens with k equal to 7. So perfectly compatible with what we observed. Not only that, I go below with g, and I still observe this multilobated structure. And to observe a structure that is not even as good as the one with g equal to 0.35, I have to let's say half the g to go. I have to go to 0.17, and it's still deformated, and the deformation is much larger than the one that I could observe with the g at 0.34 for just one step. And this is the limit that we chose for our setup, because also of resolution problem. I could go to 0.1, but I wouldn't have a resolution enough. And if I increase the number of steps, I wouldn't have had the signal to noise ratio sufficient to see something. So we have our experimental results now. We have our initial and final states, linearly polarized states, not to observe complex weak value we are not interested in. And if I choose these parameters, what I obtain that should give 18.7 as a weak value. Oh, of course, before I had with a single photopolarization, I had -1 + 1 as a eigenvalue spectrum. Here I have everything comprised between -7 and 7, because we have k equal to 7. But as you can see, all the photons fall outside the eigenvalue spectrum, and they're more or less coalesce in the supposedly right position, 18.7. Not only that, if you look at that black square there, you can find our initial single click that yielded this. The distribution can make you compute that value there, the experimental value there, that is perfectly compatible with the theoretical expectations. But look at this. Look at this single shot experiment. With one click, I'm able to obtain something much farther than the closest eigenvalue. Not only that, look at the uncertainty. I am 3 standard deviations far from the closest eigenvalue. This is unmistakably a single shot anomalous weak value, something that that is really impressive, because one of the arguments within the debate on the nature of weak values was, okay, they're just statistics. If you just accumulate, if you mix post-selection and statistics, you can obtain what, pretty much everything and so on. But this is not the case. We have no statistics here. We have just one click. We have an uncertainty associated with it. And this uncertainty is much, much lower than the distance between this click and the closest eigenvalue. Not only that, this uncertainty makes our experimental result perfectly compatible with the theoretical expectations. And this is the first time this protocol is realized. Okay, let me show you. Of course, we repeated the experiment for different scenarios, different amount of states and of G's, of course. And this is the result. These are the results we obtained. For example, let me tell you that A and B are the same weak value, in the sense that it's the same pre and post selection and the same operator, but because of the difference in G, the expected value goes from 18.7 to 9.8. Not only that, if you look at picture B, you can see the three, you can not really see, unfortunately, but you can observe a hint of the 3-lobe structure that I presented you before, although not perfectly with sloppy resolution, because of course it was beyond the purpose of our implementation. But still, all the results are in agreement with theoretical expectations. And the black square in each of them, it's the weak value, anomalous or not, related, obtained with that acquisition, the single shot one. Okay, in summary, I presented you weak measurements that can be regarded as a different approach to quantum measurement with peculiar features, overcoming some of limitations and expanding, let's say, the way in which we can perform measurements on quantum states and the fauna of results that we can obtain from quantum measurements. They can be used both for foundational and technology-oriented research as in methodology, but the interesting question is there something beyond them? And I provided you 3 answers to this question. The first one was protective measurement, demonstrating the possibility to extract the expectation value of a quantum observable from a single detection event. Then it was the time for genetic quantum measurement. That is a new protocol devised here in INRIM that is characterized by some sort of evolution-inspired mechanisms that makes the whole measurement procedure able to outperform usual projective or POVM measurements in terms of uncertainty. And finally, we demonstrated with robust weak measurement that it is possible to obtain an anomalous weak value, either in general a weak value, without relying on statistical accumulation. All these works have been obtained in the framework of a huge collaboration that is between INRIM, INMETRO, this Brazil Meteorological Institute, Bar-Ilan University with the Professor Yeo Cohen, Professor Lev Weidman from Tel Aviv University, Dr. Jan Zivier from LMU, Professor Matteo Paris from University of Milan, the detector group that is from Polytechnic of Milan, the ones that gave us the beautiful spattle array without which it would have been impossible to do all the single photon experiments, because I remind you that for foundational aspects, weak value experiments should be carried at the single photon level, because the whole formalism is at single photon level. So if you want to test the single particle predictions, you should be experimentally at single particle level, because mimicking a wave-like behavior with a wave is, of course, trivial. And Marco Barbieri from University of Rome 3. On the right side, you can find some of the papers of our group that was results I presented in this talk. And apologizing for being 8 minutes late, I thank you for your attention.
Thank you very much, Fabrizio, for this excellent talk and these nice experiments you have been performed. It is performed in your laboratory. That's good. There are a few questions. So you want to take it directly?
Let me try. I just have to bring the chat on.
Sure.
Where is the chat?
At the lower panel, you can find that there's a share screen, and just beside share screen, you have chat option. Maybe it is not directed to you, right? Maybe I can read it for you.
Okay.
Sure.
No, but okay, probably. But yeah, I have the chat, but I don't have any question on that.
But maybe it was not directed to you, I think. But yeah, it is directed to school only. Okay, let me read them.
Okay.
So there's a question by Ashish Singh. What kind of interactions we are taking into consideration for calculation of protective measurement?
Okay. What kind of
interactions?
Okay. I will just okay. In our interaction, in our implementation of protective measurement, we consider interaction, as you can see here, between the photon polarization and the transverse momentum. But of course, being this just a von Neumann coupling, this could be done for any kind of observables. I mean, this coupling here is an intraparticle coupling. I'm coupling 2 degrees of freedom of the same particle. Let's say that the polarization is the degree of freedom that should be measured, and the measurement device is the spatial wave function of the photon in this case. And it's associated with birefringent crystals. But it can be done even between 2 particles in an ancillary state. It's just a von Neumann coupling. Every kind of interaction can be part of it, a spin or whatever degree of freedom you want to associate. It's not I mean, it's a completely general scheme. We use this because we were in our quantum optics group. We had we are practical with photons. It's just that. There are no particular or preferred interactions, let's say.
Yeah. So just I have one question in this connection. Is there any post-selection involved here?
Post-selection, okay.
Each
essentially in protective measurement, post-selection is not present because we reproject onto the same initial state. So it's post-selection, but on the initial state, it plays the role of the protection. Since the decoherence is very small, the probability of post-selection to give a different result is 0. To make the state disappear, it's essentially close to 0. So it's not a proper post-selection. Post-selection should be on a different state. If you do post-selection on the same state, what you obtain is a weak average. It's like that. Because projecting on the initial state, and essentially the state outgoing, the weak interaction is 99% close to that one. So you're not really post-selecting. If you want to have a weak value, an anomalous value, your post-selection must be quite far from your pre-selection. This is not, the projection is not meant to be done in that sense. In fact, this is a Zeno-like. We exploit the quantum Zeno effect, preserving the coherence.
That's what I was just wanted to tell. Yeah, this is a kind of Zeno effect you are asking.
Yes, it's perfectly, protective measurement could be realized in two ways. Either adiabatically, that is even in the original paper of Arnov and Weidman, or with this quantum Zeno-like scheme, and that experimentally was much easier to implement. Yeah. So how many steps you did? Number of steps you have said about K equals equal to 7 because of room or space problem on the optical table, and we wanted to just have a solution without sacrificing too much, because of course the losses that I talked to you about were theoretical losses. When you deal with quantum optics, you have to deal also with optical losses. In the calculation that I showed you about the advantage of protective measurement, genetic quantum measurement on the precision side with respect to projective measurement, I didn't consider optical losses, of course, because optical losses are due to imperfections, are not due to the quantum the measurement scheme itself. And the optical losses, if you do too many steps, of course, kill you, because optical are not, I mean, they're not as good as, for example, the ones that exploit in atom physics or whatever, when splitters have 99.99% probability of doing their work. Here is, I mean, even the coating, the best coating, they have maybe some percent of losses, and if you accumulate a lot of optics at the end, you get a signal to noise ratio that is not sufficient enough to demonstrate your point.
So what was the signal to noise ratio in that case? The particular experiment is k equal to 7.
Okay, the signal to noise ratio depends on the acquisition. As you can see here, we have some noise, but we had when we had this when we accumulated the statistics, we were using some algorithms that cleaned our results from the noise, just with a noise subtraction algorithm, because otherwise, I mean, these are already clean results, or not completely clean, but close, because these detectors the detector we exploited, the SPAD array was a prototype detector, so it presented some. It was an astonishing instrument without which we couldn't have done 90% of our work, but that it presented some problems like hot pixels or whatever that should be removed and cleaned. And for the signal to noise ratio, we didn't compute precisely yet, but it was excellent. As you can see from these histograms, there was no mistake in how our results were computed. We couldn't. We just performed acquisitions long enough to get a satisfactory signal to noise ratio.
Okay, thank you.
Look, I have a question.
Yes, sure. Please.
Fabrizio, how did you physically implement that interaction, that unitary interaction, polarization with transverse moment? How did it physically happen?
With birefringence. You know that, I'm sorry for not having explained it clearly enough. But here, these birefringent crystal pairs, you know that birefringence shift one polarization, shifts one component of the polarization. Right. Essentially, with birefringent crystals, we shifted the horizontal component of the polarization, creating a spatial mismatch between vertical and horizontal polarization components. Along for example, here is the x-axis or in the sequential weak measurement, for example, it was both the y and the x-axis, because of course, if you want to have two independent measurements, you should have two independent axes, two independent degrees of freedom. And this, it's just very stringent in this case. It's it's not easy to do things properly, but conceptually, it's very easy. Of course, the crystals should be very thin, because you don't want a complete separation between the two. You just want a slight mismatch with the two polarization components still 90% or more superimposed.
Yeah, got it.
Okay, thank you. There are a few more questions. For example, Narasimha, he is asking that what is the significance of violation of Legge-Garg inequality?
Of violation of Legge-Garg inequality? Well, originally, let me go back to that. Originally, Legge-Garg inequalities were proposed as a sort of macrorealism test, saying that in the macrorealism picture, macroscopic states shouldn't be in a superposition state, because, you know, classical physics is not in superposition, and measurement should not be invasive. Essentially, these two axioms were to be present. These two assumptions, sorry, not axioms. Here we give up on the macrorealism, because of course you should have macroscopic objects to say something, I mean, about macrorealism. Testing macrorealism with single photons is simply impossible, because photons are microscopic by definitions. And this way, it still becomes a quantumness test. I have a violation, I have a purely quantum system. I don't have a violation, I might have classical behavior. I cannot be sure I'm dealing with a quantum system. If I have a violation of Legge-Garg inequality, essentially, especially in this case, with these four elements, Legge-Garg inequality, it can be considered, since in Legge-Garg inequalities, the measurements are taken onto the same single photon state, single particle or single system at different times, it can be regarded as a CHSH inequality in time instead of space. As for quantum systems, it can be considered like that. It also has the same forms. Of course, the meaning is not identical, but it's still a very valid quantumness test.
Okay. Just in this question, I have a question. For example, how did you this non-invasive measurability condition? How did you confirm it?
How the measurement?
It's a non-invasive measurability question. It's a loophole.
The non-invasive measurement. I mean, for the first term, it's easy, because IA is just the preparation. Okay, so is an average value on IB. The same holds for the third and fourth term, because I know IA and ID because of the preparation and post-selection, and ICID is just the average value of IC, because ID is the post-selection stage. This element is difficult, because IB and IC are not commuting. And how can I be non-invasive and at the same time measure non-commuting observables? By exploiting sequential weak measurements. With weak measurements, I'm not invasive by definition, because I never make my wave function collapse. So I just induce a slightly decoherence on a very faint one. And so I'm basically non-invasive. It's the best approximation you can have on measurement non-invasivity.
I mean, there are two ways to satisfy this clumsiness loophole. One is negative result measurement, and second is this weak measurement.
Yeah.
But yes, do you think both of them are actually providing us the non-invasive measurability condition?
Well, I prefer weak measurements, because with negative measurement, with negative results, you always have, I mean, you don't have something that you can really touch. While with weak measurement, you do. that's just, I'm not, I didn't investigate enough in the problem to give a decisive answer on that. And I know there's still a huge debate ongoing on that.
Yep.
But my personal opinion, I prefer the weak measurement approach.
Okay.
It's more in the spirit of the proposal, in my opinion. It's more like, I mean, in classical physics, you measure without perturbing, and you still have results, whatever. And this is exactly what you obtain with almost exactly what you obtain with weak values.
Yeah. So there are a few more questions. Question is that what constitute, I think it's a kind of fundamental question, what constitute a measurement which apparently causes the wave function to collapse into definite state?
Well, that's a very interesting but a very tricky question. Wave function collapse is one of the unsolved issues of quantum mechanics nowadays. There have been proposed wave function collapse models by Professor Lahosh Joshi, Professor Angelo Bassi from Trieste, but there could be a gravity-induced collapse. Of course, the collapse is something that can be mathematically understood, but physically it's very difficult, also because it seems to be instantaneous, and we all know that instantaneous interactions do not exist. Also, quantum mechanics is a non-local theory. Otherwise, there would be many issues due to entanglement and so on. Anyway, I'm not a conclusive idea on that. I didn't investigate the problem enough.
This is a tricky question. I mean, no one knows the answer, I think. So there's another question from Sobhadra Maiti. Is it possible that weak measurement on single photon results in phase flip noise, or will it be a depolarizing channel? I mean, the question is not...
Can you repeat, please? Because...
Yeah, it is not clearly formulated. I mean, they are actually asking whether weak measurement can be considered as a depolarizing channel or not. This is the question.
Yes, of course, they can. The weak, not the weak value, just the weak measurement. It's a sort of it's a very faint depolarization, because you're just slightly separating the two components. It can, of course. I remind you that the weak value is not just obtained from the weak measurement. You have the weak measurement, the weak interaction, and then the post-selection on the Hilbert space of the observable of interest. First, the one coupling with a pointer observable, then a post-selection on the Hilbert space of the observable of interest, and then a final measurement on the pointer or on the meter that is canonically conjugated to that. And so it's the weak value cannot be obtained as a simple depolarization, of course. But if you consider just the weak interaction inducing inducing the weak measurement and realizing the weak measurement, it can be seen as a sort of depolarization, as a sort of, more or less, yes.
Okay, one more question from Ankit Chaudhary. How can a photon be isolated for single photon experiments?
Well, you can prepare. Yeah. For example, in our schemes, we exploit a mechanism that is called parametric down conversion, in which a photon entering this type 1 crystal here in the setup produces a pair of photons called signal and idler that are produced always in a pair. I mean, you cannot observe one and not the other. And if your pump power is low, since the probability for this mechanism of occurring is about, it ranges from 10 to the minus 8 to 10 to the minus 5 or so in particular waveguides. But anyway, it's very low. the probability of producing more than one pair at a time is essentially zero. Not only that, if you put yourself on one branch and observe a click on your detector, you know, because of this mechanism, that there is one single photon, the twin photon, on the other branch. If you collect it properly, then you have a certified single photon each time your SPAD, your single photon avalanche diode, on the correlated arm clicks. And this is useful. Furthermore, we certified our single photon source because we computed the G2 at the out of the source with a Hembury, Brown, and Twist interferometer, and we found it was 0.1, 0.13, more precisely, plus minus 0.01. So perfectly in the single photon regime, since everything below, let's say, 0.2 is considered single photon. Of course, a pure single photon should be zero, and it's not the best single photon source that we obtained here. In our labs, we obtained a single photon source, a fiber single photon source in the 50-50 regime, in the infrared regime, that showed a G2 of 5 in 10 to the minus 3. But still 0.13 is okay. To say it's okay for saying that this is a single photon. Also because 0.13 was without any dark background subtraction. So probably the value would have been even below 0.1. Of course, there are other mechanisms. There are single emitters like diamonds, like Bloor centers in diamonds, quantum dots, and other methods. But here in our labs, we usually rely on diamonds or parameter conversions.
Okay. So maybe the last question. From Sayantan Das, can some sort of analog of protective measurement be realized in classical optics regime as was realized in weak measurement? For example, in beam shifts.
Of course it can. We realized, as I told you before, if you repeat those experiments with a laser, aside the fact that you cannot measure a single click, but you obtain the same results, the same distributions. Because what you're sensing in this case, in this implementation, is a wave-like behavior of a single quantum particle. If you mimic it with a wave, of course it's perfectly logical to obtain a wave-like behavior. You're using a wave for simulating a wave-like behavior. It's logical to obtain that. Of course, you can obtain this with a laser. Definitely. But you're not anymore using a quantum system. Of course, you're not allowed to say you're quantum.
Yeah. So let's maybe the one more question. It's from Radhika. She's asking that your protective measurements give one shot expectation value as result, right?
Yes.
Would you say this probes some classical feature of the system?
No, it's not that. It provides you some sort of statistical information, but it does not mean that your system is classical at all. You're still you're still at the single photon level. You're still measuring single photons. You're not classical. You're not transforming your states into classical states. You're still doing everything at the single particle level. So it's saying, if you remove the protection, you still observe your single clicks on the on your screen, each one on one of the positions related to the eigenvalues values of your observable. You're not transforming your system into a classical one at all.
Yeah, that's true. So, Professor Panigrahi, you have anyone want to ask questions?
No. Such a beautiful talk. Fabrizio, thanks a lot.
Yeah, thanks a lot. It's an excellent talk. Yeah.
Thank you for inviting me. And
yeah.
Okay, I leave room to other presenters.
Yeah, thank you so much.
Thank you very much.
Thank you.
So Alok, we think now we take a break for tomorrow.
Yeah, tomorrow.
At evening time, there will be tutorial by because we don't have to be there.
Yeah. Sure.
I will just see for some time how is he doing, and then tomorrow you will be the moderator, right?
Let me just take a look in the schedule. It's a first talk. Yeah, first talk will come to the hall talk, so that I will be there at 10. And then I think these things you may take care with the other moderator.
Chiranjeev is moderating. Chiranjeev is moderating one. Saurin is moderating
12. No? Mine is from 12.
Yours
Yeah, it's a Delatore.
Okay. Bar Ilan University. Chiranjeev.
Right.
You are moderating. You are moderating for. You got it, na?
No, Soren called me and told me.
Saurin is moderating.